This poster contribution includes a comparative study of superparamagnetic magnetite nanoparticles with different shape and microstructure. Single-core nanoparticles have been prepared by thermal decomposition of precursor in high boiling point solvent using oleic acid as stabilizing agent. As precursor, these two reactants were used. By this synthesis method, magnetite spherical nanoparticle with diameter of 15 nanometer and manganese iron nanoparticle with major dimension 18 nanometer have been obtained. In both cases, the particles are crystalline as indicated by the high resolution image, the order and spacing sequences corresponding to the different crystallographic plane. Multi-core particles have been prepared by co-precipitation process using sodium acetate as precipitating agent and ethylene glycol absorbent for the synthesis of the magnetite functionalized amine sample, ethylene diamine. In the case of the magnetite 26 sample, the synthesis was carried out under exothermal conditions at 200 degrees centigrade for 20 hours. The next transparencies represent the nanocluster of amine functionalized magnetite are of 70 nanometer inside and are formed by a core of 6 nanometer. The size of the core has been obtained by a contrast profile with the digital micrograph. The contrast maxima are separate from each other approximately by 6 nanometer. The magnetite flower shape assembly of 70 nanometer formed by 26 nanometer nanoparticle have been also prepared. In both cases, the individual crystal forming by nanoflower and nanocluster are attached in a common crystallographic orientation as observed in the high-resolution microscopy image. According to that, the X-ray diffraction shows narrow maxima. Also, the magnetite 26 sample representative of multiple assembly, not of an individual core. Show that in both cases, the orientate attachment of the particle can be related to a slow nucleation at low processes. In magnetite 6NH2 sample, the concentration of OH groups on the surface of the particle should be low, since the water present in the reaction medium only comes from the hydration of the precursor. Therefore, the growth of the particle must be slow. In the 26 sample, the role of ethylene glycol is also as reductor, but is a weak reductor, and the formation of the growth is slow. In both cases, the nanoparticles have enough time to rotate, and most of them in the assembly have the same crystal orientation, minimizing the energy surface. The magnetic properties indicate, in all cases, the presence of interparticle interaction in our sample, have suggested the broad maxima found in the zero field couldn't cure, although the most of the energy barrier are overcome at low temperature. The cure I are indicative that the superparamagnetic regime stands in a broad range of temperature. For a stabilized nanoparticle, this result indicates that the oleic acid doesn't prevent the dipolar interaction between these particles. For multicore particles, the orientate group probably favors the magnetic interaction across the interface. If so, the effect of the surface Kant spin is minimized, and this can be the result why the value of the magnetization for the magnetite functionalized sample with the smaller particle size is the highest, close to the bar magnetite value. Both multicore particles present the higher magnetization saturation values. The heating capacity of nanoparticles in the present alternate field had been evaluated from the magnetic hyperthermia measurement using the calorimetric method. This amount of heat generated by magnetic particle had been quantified by the SAR values obtained from the heating curve using the initial slowed method. The measurements were made with the particles suspended in water at different frequencies and magnetic field. Comparing the stabilized sample with similar particle size with the SAR value for the manganese iron Q-like particle can be related to the said anisotrope. In both samples, the behavior is the result of the individual core, although the efficiency of the heating can be affected by the interparticle interaction. However, in the multicore particle, the collective behavior is probably responsible for the high relative SAR values. This collective behavior of the individual particle with the anisotropy axis aligned can increase the anisotropy of the system and the efficiency of the heating. This collective behavior can be understood as a result of the interacting cluster of the interacting particle.